You can talk anyway. I mean, who watches these? Who watches? Jerry watches.
Jerry.
Shout out, Jerry.
Wait.
So, I'm sorry, I'm going to give you a shout out. Shout out, Luke. Luke, shout out.
We forgot to go see what Jerry said.
I don't think he hasn't said anything. I haven't
You said he said more, and then he never went and looked.
I said he was going to get us, he was trying to get you guys a free day.
Yeah, we want to see the first. We didn't see the evidence.
You need to see the evidence.
Yeah.
Here you go.
Watch him be like, give them a day to play baseball. And he'd be a real G at that.
Colin's tractor. Shout out, Colin. I think that's Colin McLaughlin. I think. Jerry. Yeah, give them a free day.
Oh yeah, I agree with Jerry.
What did Caleb say?
You go to this school. Oh. Okay.
This is
Caleb goes.
that's Fuller. That's Jack. This guy.
Oh, okay.
Wait, do you
Hey,
go to
Jerry, you seem to have missed my comment on a previous video, so we should repeat it.
By the way, you made an appearance on the most recent Library.
So be sure to check that. Ow, my last comment. Hello, Jerry.
What?
I've noticed I've been talking. I've been, what does it say? I've
Taking
been
an interest in Rel.
Would you mind recording and by giving a shout out on your channel with nearly 250 members? Thank you for your consideration.
I don't really post videos on this channel anymore. I just
Wait,
use
have you
it.
posted a video?
I reckon I can make a YouTube post.
Go to it. Go to it.
No, he hasn't done it.
6-sucker challenge.
He lost his friend.
Yeah. It's a bummer.
Maybe tomorrow.
Wait, did you watch the 6-sucker
Maybe.
video?
Maybe.
Here's the magic school bus.
It's all started from that one comment.
I was when you were so confident in the other one. I'm like, no, you have to change it.
I know, that was a great response. All right, so here's 12, 14. Here's 16 and 18. Don't worry where it says possible rational roots. Possible roots are. That's one of the things that we're going to learn today. We're going to learn about how to figure out what the possible rational roots could be. All right, there's 16 and 18. And here is, well, I'll just leave it. Anybody still need 16 or 18? Again, I'm not too worried about the factored part. I'm worried about the end result, right? The solutions are. Okay, let me scroll it down a little bit more. Here's 24 and 26. Looks like 24, if you had pulled out the 4 first, it looks like it would have factored by grouping. I'm wondering if you would have pulled out the -1 first, if it would have also factored by grouping. But at any rate, it does factor by grouping. You get the x squared plus 9 in the end, which is a plus or minus 3i. Don't forget about the i's. If you've got a negative, and then you're trying to take the square root of it, it's going to turn out to be an I. Number 26. Here, take a look at number 26, because there's hardly any work there. And here's the reason. If you go to graph 26, and I see an x to the third plus 3x squared plus 3x plus 1, and I go to graph that, what happens at -1? Visually, what happens? It bends through, correct? It bends through at -1. So how many possible roots could there be? Well, there could be we know it's odd, so it's got to be a 3, a 5, a 7, or a 9. But now we can pair that with the knowledge of the fact that, okay, if it's an x to the third power, how many roots are there going to be? 3. So could this possibly be a 5? I'm supposed to be a 5 at that bend. No, it could only have the possibility of being a 3. So if I see a bend at -1, I mean, it would be a good idea to just check to make sure it's at -1, but then you know that it's got to be all 3 if it's a cubic at -1. Let's keep scrolling down a little bit. Here's 28 and 30. Again, you can kind of ignore the possible rational root stuff right now. Anybody have a nice long weekend? Catch up on sleep. Catch up on. Oh, you guys laugh at that? Like, no.
No, because nobody answers.
That's my daily life.
Did you have a nice weekend?
I did, thank you.
What is 4 things you did this weekend?
4 things? Man, did I really do 4 things?
Yes.
We built a snowman.
Aw.
What else did we do? I got out my old Xbox 360 because we had like the Connect thing where you could like walk around like it'll catch you. And we set it up for my 4-year-old and she loves it. Pretty cool. You get Whitewater.
When's the vlog coming?
I know I'm gonna do that. I did not do my 100 subscriber special. So
We're gonna start losing followers.
I know. Seriously, what if it gets below us?
We might not. I'm gonna start. I'm gonna.
You're gonna subscribe.
Yeah, never promised something and it's been months.
I know. That's the end, right? 34 is the end?
Yeah.
What else did I do this weekend? That's Chinese food.
What'd you say?
What's Chinese food? I always get General Tso's chicken and an order of crab rangoon.
That's really what I got.
Really?
Twins. I like their Mongolian beef.
I don't know. I like General Tso's, and I'm not a person to like deviate away from what I like.
Just simple, man.
I see.
That's okay.
Yeah.
All right. Any questions for anything on this homework assignment? Any questions? All right. Okay, so there's no guided notes today because there's not really any notes to write down. I'm just going to be writing down example problems and then doing them. With the exception, we got to talk about this whole rational root theorem. But not many notes to take today, just some examples to do. All right, so we looked at on Friday how to create a polynomial with the given zeros. However, every single example that we did, the zeros were rational. The zeros were whole numbers. Well, I shouldn't say whole number. They were just rational. There were some with some fractions. But what if, is life always that easy? No. We have polynomials where we find the roots and they turn out to be irrational. They turn out to be non-real. So how do I work with that in terms of figuring out what the polynomial is? Like, for example, here. We got 2 plus I, and then the square root of 3. Well, way back when, I kind of glazed over it a couple sections ago, we had this thing called the irrational root theorem. The irrational root theorem. It said that whenever an irrational number is a root, the conjugate is also a root. We can also expand that to non-real numbers. Okay? So, for example here, if I know 2 plus I is a root, then I know 2 minus I is also a root. Okay? So if I have 2 plus I as a root, I know that 2 minus I is also a root. It was equal to x, not 0. We get it equal to. Oh, and that looks good. I'm sorry. I'm going to flip that around. I like x on the left side. 2 plus or minus I is equal. Oh my gosh. What the heck? Somebody's got a case of the Mondays, even though it's Tuesday. 2 plus or minus I. The irrational root theorem, and notice that the square root of 3 is an irrational number. The irrational root theorem said that if you have an irrational number, then the conjugate is also a root as well. Like you can't have one without the other. Well, in this case, it's just adding in the plus or minus, because we assume that it's a positive root, positive square root of 3. So it's not just a positive square root of 3, but also a negative square root of 3 could also be a solution there. Now, whole numbers don't work like that. Whole numbers, they're just straight up, that's the root. You don't always write plus or minus. That's the whole number. All right, so what should our final power on x be? Should it be 3? No. It should not be 3 because the plus or the minus are two separate roots. So I ask again, what should my final power on x be? What should my final degree be of it? 5, right? Now let's see how this works. Here's the method that I like to do on this. Now, if you have friends in Mrs. Apple's class, she's going to teach them a little bit differently. Okay? She's going to teach them a method that I'll probably show you somewhere along the line. In my opinion, it requires just a little bit more work, but it's pretty similar. But here's the method that I do. I like to simplify so that the square root is completely alone. Like for example here, x minus 2 is equal to plus or minus I. Now, what do I mean by square root? That's just an I. Well, remember the square root of -1 is I. Right? So that's like saying x minus 2 is equal to plus or minus the square root of -1. Right? Because I is the square root of -1. Again, the goal here is to try to get everything over to the left side. Right? So if I'm trying to keep moving things over to the other side, how do I make this square root go back to the other side? How do I undo a square root? Square the opposite side. And that takes care of the plus or minus that was sitting on the outside, right? If I work backward, if I undo these steps, that plus or minus would, show up there if I'm working from bottom to top. Well, I've just got to figure out what x minus 2 squared is. Remember, that's x minus 2, which is x squared. Outer is a -2x, inner is a -2x, minus 4x, -2 times -2, positive 4. And now I can finish it off to add the 1 over to the left side. X squared minus 4x plus 5 is equal to 0. Because that was the goal, right? The goal was to try to get it equal to 0 so that I can write it as a factor. So this is the factor that corresponds to the roots 2 plus or minus I. Okay? If I were to work this backward, if I were to solve x squared minus 4x plus 5 and try to find two roots that add together to, or to find the two roots, I would get 2 plus or minus I. Now, let's take a look here. For my second root, this plus or minus the radical 3, is the square root simplified? Is the square root alone? Is it isolated? Yeah. And at that point, that's when we can square the opposite side. X squared is equal to 3. It's nice when there's no number up front with the plus or minus, because then we don't have to FOIL like we did here with the x minus 2. Now all I have to do is just subtract the 3 over to the other side. And now all I have to do is just subtract the 1 over to the other side. So here are my factors. I'm only half done with this problem, because this is not just what are my factors, this is find the full polynomial. So my f of x is going to be, I'll write it over here in red, f of x is going to be x squared minus 4x plus 5, x squared minus 3, x minus 1. And now we got to multiply this all out. Let's go for it. I'm going to multiply the far right side first. I'm going to multiply these two together first. So f of x is going to equal, let's bring this down, x squared minus 4x plus 5. And now let's FOIL this. First is my x to the third. Outer is my minus x squared. Inner is my minus 3x. Last is a positive 3. And now we multiply the trinomial into the polynomial, the 4-term polynomial. Okay, let's bring in x squared. X squared times x squared times x to the third is x to the fifth. X squared times negative x squared is a negative x to the fourth. X squared times negative 3x is a negative 3x to the third. X squared times positive 3 is a plus 3x squared. Let's bring in my minus 4x. Negative 4x times x to the third is a negative 4x to the fourth. Negative 4x times negative x squared is a positive 4x to the third. Negative 4x times negative 3x is a positive 12x. Negative 4x times a negative 3 is a negative 12x. I'm going to run out of room. I'm going to move this over a little bit. And now we bring in the 5. So that's a plus 5x to the third minus 5x squared minus 15x plus 15. And now we combine like this. So f of x is equal to, and this is going to be our final answer, x to the fifth, that goes away, minus 5x to the fourth, and those go away. I've got a 3 here, an x to the third, an x to the third, and an x to the third. That's negative 3 plus 4, so 1 plus 5 is 6, x to the third. Looks like I've got x squareds here and here. So 3 and negative 5 make negative 2 x squareds. Okay, I've got 3 x's here and here. Those cancel. 12x and negative 12x, and I've got a negative 15x. And then plus 15. And if you were to solve that, if you were to find the roots of that polynomial, you would get 2 plus or minus I, the square root of 3, or plus or minus the square root of 3, and then negative 1. Or was it negative 1 or positive 1 when we started? Positive 1. What did we say at the very beginning? How many roots? What should be the degree on x? 5. Were we right in the end? Yeah. Questions about that? Let's do another one of those, shall we? Okay, I've got 2i, 1 plus radical 2, and 3. Now, any complex or irrational roots, I'm going to say this again, any complex or irrational roots must include the conjugate as part of your zeros, as part of your root set. So, for example, here, this is an irrational root. I'm going to have x is equal to plus or minus 2i. I'm going to have x is equal to 1 plus or minus radical 2. And then here, I'm just going to have x is equal to 3. You can't forget about the conjugates, because that would decrease my amount of roots by 2. I really am going to need an x to the 5th power in the end here. I'm really going to have an x to the 5th power in the end here. All right, so let's whittle it down a little bit. I'm going to change this I into the square root of negative 1. So plus or minus 2 square root of negative 1. And now, what I want to do here is get that product that's sitting in the outside, that 2 that's sitting in the outside. I got to get it back underneath the square root because I'm working backward, right? You know, the previous step to this would have been if that 2 was back inside that square root. So what does that become on the inside? Negative 4. Negative 4 on the inside. This would have been x is equal to plus or minus the square root of negative 4. Because doesn't that simplify down into 2 times the square root of negative 1, which is plus or minus 2i, right? So you're working backward. You keep trying to put things back underneath the radical. And now, once my radical is completely isolated, I square the opposite side. It takes care of the plus or minus. X squared is equal to negative 4. So x squared plus 4 is equal to 0, which is my root, or my factor, excuse me, my factor that corresponds to the root, plus or minus 2i. And that 4 is installed out. Okay. Let me see, if I hit stop and then play again, will it work? Stop, play. That didn't. Now, for my middle root, the 1 plus or minus 2i. For the ones where you have the number and then the plus or minus and then the radical of the I, that's the one where you have to subtract the 1 over to the other side and then deal with the radical. Which makes life a little bit more difficult because now I say, okay, x minus 1 squared is equal to 2. And I have to FOIL that. Right, that x minus 1 squared becomes x squared minus 2x plus 1 when we FOIL it. Guys, if you're one of those people like shortcuts, whenever you square a binomial, it's square the first, double the product, square the last. Okay, square the first, double the product, square the last. I square x, I get x squared. I take the product of the two, negative 1x, I double it, make it negative 2x. Square the last at positive 1. And then I subtract the 2 over to the other side. X squared minus 2x minus 1 would equal 0. And that's the factor that corresponds to the root, 1 plus or minus equal 2. And then we can just have x minus 3 hanging out over here. And now we multiply all of these together. Okay? So this is going to be f of x is equal to x squared plus 4, x squared minus 2x minus 1, x minus 3. I don't know. Let's multiply my last two together. I don't know why I like looking from right to left when I multiply these. So I've got f of x is equal to x squared plus 4. And then we've got, okay, x squared brought in x to the third minus 3x squared. Bring in the negative 2x. Negative 2x squared plus 6x. Bring in the negative 1. Negative x plus 3. Simplify. X squared plus 4. X to the third minus 5x squared plus 5x plus 3. And now I'm multiplying the x squared plus 4. I'll multiply in the x squared. I'll get an x to the fifth minus 5x to the fourth plus 5x to the third plus 3x squared. I'm multiplying by 4. I get a 4x cubed minus 20x squared plus 20x plus 12. And now we combine my terms. I've got an x to the fifth minus 5x to the fourth. And then I've got, looks like 9x cubed. And it looks like minus 17 x squared plus 20x plus 12. And that is f of x. I could plug this in to my calculator. I would see the root at 3, and I'd see it cross somewhere weird. No, I didn't think it. Yes, I did. No, I did. Hi, Mr. Kastner. Yes. In the old ones? I don't know. I haven't checked that. I would check for 9%. Yes, sir. Sorry. Okay, questions about that one? We good here? A lot of work. You know, it's only get compounded by the fact that we've got irrational and non-real zeros. That's a bummer. Right. All right, last thing we're going to talk about within this set is called the rational root theorem. Let me ask you guys this. You know, on your homework over the weekend, if you couldn't factor something down, where would you have to go once you've exhausted all of your possibilities to factor? You would have to go with your calculator, right? You would have to. So what if you didn't have your calculator, right? What if you didn't have your calculator? Well, you would have to rely on this thing called the rational root theorem. Now this says that if the polynomial p of x has integer coefficients, then every rational root, now integer coefficients meaning the numbers next to the variables from my polynomial all have to be integers, positive and negative whole numbers, no fractions or anything like that. If the polynomial p of x has integer coefficients, then every rational root of the polynomial equation, every rational root, and notice how this is only saying rational root. This will only ever get you rational roots. It will not include irrational roots. You'd have to find it in a different way, or complex roots. You'd have to find that in a different way. If the polynomial function has integer coefficients, then every rational root of the polynomial equation can be written in the form p over q, where p is every factor of the constant term, meaning the last term, and q, come on now. Hi, Mrs. Brown. I'm doing well. How are you doing? Oh, I forgot to mark Jenny's absence, didn't I? Yeah, I'll do that. Thanks. Yeah, bye. All right. Hopefully there's no more stuff. There will be. So P is a factor of the constant term, and Q has to be a factor of the leading coefficient of P of x. Okay? So what am I talking about here? In terms of this polynomial, every rational root is of the form one of the factors of my last divided by one of the factors of my first. Okay? What do I mean here? Let's take a look at this one. My p-value is 2, right? And I get 2. I notice it's deceiving here because my leading coefficient and my constant term are the exact same thing. That's where I get my p-value. My p-value is my 2. My q is also 2. And that's from that. Now, this rational root theorem says that I have to list off all of my factors of p. Well, every factor of 2, 1 and 2, that's an easy list, right? My factors of 2 are just 1 and 2. But we also have to include both positives and negatives. Because isn't it just like if I multiplied negative 2 times negative 1, wouldn't that still result in a positive 2? Right? So positive 2 would have to have factors of plus or minus 1 and plus or minus 2. So same thing here. Okay, so that means my P over Q list looks like this. I have to take every single member of my P list and divide it by every single member of my Q list, both positives and negatives. Like for example here, let's take positive 1 in my P list. Well, I would say positive 1 over positive 1. I could take positive 1 over positive 2. Right, positive 1 over positive 2. I could take negative 1 over positive 1. I could take negative 1 over positive 2. And that's exhausted my plus or minus 1. I could take positive 2 over positive 1. I could take positive 2 over positive 2. Well, what is 2 over 2? 1. So it's already on my list. It's included already. I could take negative 2 over positive 1. I could take negative 2 over positive 2, which is already included in my list. Now, what does that mean? That means that those 6 possibilities, yes, I say 6 because I have plus or minus, those 6 possibilities could possibly be my rational roots. At this point, you really hope that you're a good guesser. Because are there actually 6 roots to this polynomial? No, there's only 3, right? There's only 3. So only some of them on this list are going to work. So what do you have to do at this point? Well, you just got to throw something at the wall and hope it sticks. Let's check 1. Okay, let's check 1. Let's see if 1 is a root. You got to hope to get lucky. Don't forget your 0 in there. Let's check 1. Well, that's 2, a 2, a negative 7, a negative 7, a negative 7. Is that one going to be a root? Nope. So you know what I do? I kind of cross that off my list, and I erase everything from there. I kind of say, okay, positive 1 is off my list. You want to try negative 1? Let's try negative 1. Right? It gives me 2, a negative 2, a negative 11, a positive 11, a positive 11. Is that going to work? So my 1s are gone. I don't really want to do 1/2. Let's try 2. Gives me a 2, a 4, a negative 5, a negative 10, a negative. Is that going to work? So positive 2 is off my list. Let's check negative 2. Positive 2, negative 4, negative 13, negative 13. Wow. And none of those work? I really hope some of these work. Let's try 1/2. We bring down our 2. We got to be 1, negative 8, negative 4. Bingo. We got it. Okay, what does that mean? That means that x equals 1/2. So let's just say x minus 1/2. We could say 2x minus 1 if we really wanted to. And then we've got 2x squared minus 8x minus 4 equals 0. And now we try to whittle it down. Because it's a quadratic, I can now use the quadratic formula or completing the square. Let's pull out that 2 before we do anything else. 2x minus 1/2, x squared minus 4x minus 2. Now, does that factor? No, which makes sense. Because if it factored, there would be more rational roots that exist. And there's not even enough to go on my list. I checked all the other ones it could possibly be. So let's complete the square real quick. We got this x equals 1/2. And we got x squared minus 4x. Let's put the plus 2 on the other side. Half of negative 4 is positive 2. Or sorry, negative 2 squared is positive 4. So add 4 to both sides. Which leaves me with an x minus 2 squared is equal to 6. I square root the opposite side. And then I add the 2. So here are my 3 roots to that cubic equation. Did we use our calculator at all? No. Why didn't 2 plus or minus radical 6 show up on my list? It's irrational, right? This is the rational return. That P over Q list will only ever show you rational roots, and that's it. It will only ever show you rational roots. Yeah. Remember, the only time a GCF would ever be a root is if it was with an X. Since it's just a whole number, you just kind of let it go. Yeah. I'm not going to go through the whole problem, but just kind of show you one more list, one more P over Q list. Guys, you guys are going to love me when there's a 1 out front. Okay? It's going to be nice when there's a 1 out front. Here's why. My P value is a -3 and my Q value is my 1, right? The nice thing about the 1 is that, okay, my factors of -3 are plus or minus 1 and plus or minus 3. My factors of 1 are just plus or minus 1. So when I go to make my list, my P over Q list of possible things that I'm going to test out that would be solutions, look, I've got 1 over 1, -1 over 1. So plus or minus 1. I get 3 over 1, -3 over 1. Plus or minus 3. So in essence, when there's a 1 out front, my P over Q list is the same thing as my P list with my factors in it. When there's a 1 sitting out front. Okay. So there's 4 possibilities. You just hope to get lucky and get that correct root that it turns out to be a 0. Okay. All right. Sorry, running low on time. See everybody at home. Sorry for all the distractions. Shout out, Jerry. Shout out.